Hello everyone. In this video we'll be discussing about columns. We'll be looking towards the issue of different structural members that faces a vertical load, especially when the load is vertical. Then what happens to that structure? So you have seen such type of structures in which actually connects the floor to the roof, and they take the load of the roof. Most of the in most of the cases this happen that the roof load is taken by the columns. So such type of members are usually called as columns. They take compressive load, and since they take compressive load, they are subjected to different types of failure conditions. These are two types of failure conditions we will be discussing towards that. So a particular load that the column can take, this is known as a critical load. We'll be discussing more about what exactly critical load is, and then based on the type of columns, we have two types of theories emerging as Euler theory and a Rankine theory. So mostly the Euler theory is for some specific types of column which are usually called as long columns, and Rankine theory can be used for long columns and short columns both, but mostly it is used to design for the short columns. Then we have a very important concept of a slenderness ratio, which actually distinguish between two different types of column, which is a long column and short column. So we'll be discussing what exactly column is, and we'll be taking towards all these topics in a very concise and precise manner. So a column is any structural member that takes up the vertical loads or the axial loads basically. So this type of columns you have seen, which actually supports the roof. The load of the roof will be here, and this is a floor. So it actually is a supporting member between a roof and a floor, between your roof and a floor also. And such members are columns. They are not beams. Beams takes the load in a direction of the displacement. So you have seen that these are such type of like simply supported beam this way. When they takes a load, they deform in this direction only. So they takes the load in the direction of the deformation. However, in this case, when the load is occurred from the top it is being loaded, and then it takes the load. It takes the load from the top, and this is fixed at the ground at one kind of a boundary condition for a particular column. Now based on this this height of this column is very important. Actually, this is also called as an effective length of the column. So the height of the column is very important. You have seen that usually the distance between the roof and the floor is usually most of the cases it's 12 feet or 10 to 12 feet. But in some other cases you have seen there are very long columns. So even if the columns that are there in the commercial household, when they fail, we don't want any such column to be failed, but in most of the cases, if you have seen that such types of things fail, they fail by crushing. They fail by crushing. Whenever the load is at the max to them, they fail by crushing occurring inside the column, and the kind of crushes. So these are technically considered in the regime of short columns. They are considered in the regime of short columns. However, there are some large columns also that basically takes up the load to an extent, and they usually fails by certain type of deflection, which is when such column is loaded, they fail by a certain type of deflection which is out of the axis of the load. Out of the axis of the load. Out of plane deflection. So these types of columns are usually considered as a long columns. So now it's important that there must be some criteria on the basis of which these two columns may be classified, they may be differentiated. So usually what happens, they are termed in terms of the slenderness ratio. This example, we'll talk more about the slenderness ratio in the later part of the video. But at this point of time, I would like to tell you that what is the slenderness of a structure. Like this is a column, like this is a specific column for you. So it has particular dimension, and a length. So if I have something with same dimension and more length, that is more slender. If I have some wire which is very thin, and you know that the thickness of the wire is very small, it is very long in length. The wires, the electrical wires that we have, they are very long in length and have very small cross section dimension. So these are very slender. The more cylinder that you have, the better it is. So they are known as slenderness ratio in the terms. You have seen when we used to when there is a construction of the roof, then you have seen there are these small struts that have a very long length, have a small circular dimensions that are used on the top of the roof, that are placed in the cross-sectional manner, that are placed on the top of the roof during the construction. They are very thin, and they are cylinder. They are placed like this in a matrix form, so that the structure can take the load even after once the bamboos are removed. And then they used to put cement and that paste on top of it, so that becomes more and more contractile. So such type of thinness of the member is basically an indicative of the slenderness of the member. So if the member is more cylinder, it is usually considered as a long. So such type of loading conditions is like when the load is from the top. So you can consider them as a short and long columns. Now how will you demarcate between a short and long column? So usually we take up one thing like the length of the column, divided by the least dimension. This should be smaller than 12 for a short column. Smaller than 12 for a short column, and this should be greater than 12 for a long column. Greater than 12 for a long column. So what is length upon dimension? Length means like this is the length of the structure. Let's say this is 100 mm, and then the cross section, let's say the cross section is rectangular in shape. So this is 8 and this is let's say 4. So the length will be, the ratio will be, this ratio is 100 upon the least dimension is 4. So this is approximately 25. This is 25. So this is greater than 12. So this comes under long column. That depends upon the basically the cross section of the member. If the cross section is circular, take the diameter. Diameter is the same, the least dimension only. for rectangular, for circular, for different types of cross section, take the least dimension, divide by them. Now the another question that comes to your mind is, what is this 12? Why this 12 is it? 12 is the slenderness ratio. Basically it's the magnitude through which we demarcate between long column and short column. We demarcate between a long column and a short column. So on that basis, basically, if the ratio of these two dimensions is greater than 12, we call them as a long column. If it's smaller than 12, we call them as a short column. So now we can now say that we know how to distinguish between a short column and long column. So if there is this type of vertical load existing on the structure on this type of short column, so short columns usually fail by crushing. What is crushing? Crushing is, like as I said, you have seen some buildings are being crushed. So if the building gets very much old, in US, in Russia also, in many places, when the building gets very old, so what they do, used to pull it down, bring it down. So they used to crush it. They do not used to bend it like that and then drop it. They used to crush it. So they used to put some vertical loads on top of it, and then it can be crushed like that. Or you might have seen the collapse of 9/11, the building of World Trade Center. When it collapsed, it basically collapsed by crushing. So that crushing stress that is required to crush this member is basically a stress that requires to crush this member, is what is the crushing stress, sigma c, and that is simple load upon area of the cross sectional member A, area of this cross section of the column. So usually short columns are fail by crushing. And what happened to the long columns? Something very different, by which we used to discuss and study the behavior of columns. The long columns fail by buckling. That means this is a certain kind of deformation that happens against the direction of load. Whenever you put a vertical load on such type of columns, on very long columns which have slenderness ratio of more than 12, in that cases these columns fail by a bending of certain kind, which are known as buckling. It is one kind of a phenomena by which a column basically fails by a combination of two types of failure conditions, which is one condition is a bending and another condition is a compression. So during the buckling, a structure fails by bending and compression. So a combination of these two for a particular long column is known as buckling. It's a phenomenon by which usually a long column fails by a combination of these two conditions, a bending and a compression. Usually as the axial load is increased, the columns tends to buckle or bend. So once the axial load increases more and more, these long columns tends to buckle. For smaller value of the load, the columns usually remain stable, equilibrium, and they usually remain straight. However, for a higher load, if the axial load is very much higher, for certain long columns, this exists that they used to buckle. They used to kind of dance in this fashion or in this fashion. Okay? They used to dance in this. They used to put it, a kind of bend it in this direction, or they kind of bend it in this direction. For long columns, for short columns, a crushing occurs. They are kind of crushed like a pile of biscuits. If there is some kind of a pile of biscuits, in this fashion. And if you would be interested in putting some axial load from the top, then this, as you know, these are brittle in nature. The biscuits are brittle in nature. They kind of fails by crushing, and they are kind of crushed. Everything is kind of crushed. So however, for some longer columns, they fail by buckling. This is, I would like to tell you, this is important actually. So what we are basically interested in, we are interested in knowing the load, which is basically a particular critical load which is required so that the buckling does not take place in structures. The buckling does not take place in structure. So basically we are interested in avoiding this condition of buckling so that we will be able to design long columns in more appropriate manner so that they do not fail. And even if they buckle, there may be some troubleshooting mechanism that may take place, and that may make up proper corrections to this such type of loading conditions. So we are mostly going to study about long columns, and we're going to study this failure condition called as a Euler theory. So on first condition, we will be interested in knowing the critical load, the load that is required before the column buckles. A critical load that is required. You also would be encountering such type of load is also known as a crippling load. A crippling load. So a critical or a crippling load required just before when the column buckles. So we are mostly interested in this, and the theory, or the Euler theory. Euler theory says that and the Euler theory actually says that such type of condition, Euler theory gives the this critical load P critical as n square pi square EI upon L square. Now now there is many terms that requires an explanation, and you would also like to know how this expression is obtained. How this expression is obtained, that is also important. So we'll do a simple quick derivation here. First of all, we will try to obtain the expression of P critical. So this will be the critical load. This will be the critical load that is required for a certain type of column, and as you can see in this expression, it includes the length of the column. That means the length should be coming in the consideration. Further, a moment of inertia is also coming in the consideration. This is moment of inertia, and further you will be seeing that there are in a plane there are two moment of inertia along the x-axis and along the y-y, and you will be seeing that this will be the least moment of inertia will be considering for crippling load, because for a particular least moment of inertia, the load will going to buckle. The column will going to buckle for this load. So requiring the least moment of inertia. Further, requiring the modulus of elasticity. That means the material property is required. That means the material property E for this material is required to obtain the crippling load. And then we require a pi and n. So we'll be looking towards how this pi and n how they have been in this expression. So if there are two columns of the same nature, that means having the same material E. So the important thing is that I for these materials will be different, and the length of these materials, these columns, long columns, will be different. So these are the two important conditions, I and L. And if there are same columns with different end conditions, that means the length of the column is same. With different end conditions, we will be mostly concising ourselves towards this E. That means for different end conditions, this L will be different. We will be talking more about this theory But before that, let's kind of derive this expression. It will be important. Quickly, I'm going to derive this expression for you. Now take a beam like this, and take a beam, a column basically, which is fixed in this fashion, and now I'll going to represent the column by a simple line. So this simple line, when gets a particular critical load, it kind of deforms in this fashion. Okay, so at any particular distance xx from the top, from the point of application of the load P, let the transverse distance y as this. So at any distance x from the top, a particular deflection is seen at a distance of y. So let's take out this particular part of element and let's analyze this. So at this particular point, this is distance y, this is x for you, the overall length is L. So at this load P, there will be a moment existing, M, a anti-clockwise moment. So, and then there is a moment occurring because of this load also. So the moment, the summation of all the moment must be equal to 0. So your moment mx, let's say, plus your p times y will be your moment also. This will be equal to 0. Now you know that the elastic part of the curve, this moment basically can also be written as ei d square y by dx square. This is the equation of the elastic curve. This is elastic curve, the equation of the elastic curve, ei d square y by dx square. So d square y by dx square. So this equation, this is also you have seen in the bending of beams, deflection occurring due to the beams. Ey is equal to 0. Equation for the elastic curve, elastic nature of the beam, and we are considering that this is not linear. This deformation or the buckling occurring here is occurring on a particular variation. That means d square y by dx square. This is kind of a slope to this. So the solution to such type of equation, we can also further make this equation in a proper way. D square y by dx square, a differential equation of the second order, p upon ei y is equal to 0. So the solution for such equations basically can be drawn to be as y is equals to c1 cos square root of p upon ei. The p upon ei is the coefficient here, p upon ei, and times x plus c2 sine square root of p upon ei again times x. This is the solution to the differential equations. This is the solution to the second order differential equation. Y equals to c1 cos square root of p upon ei x plus c2 sine square root of p upon ei x. Now the condition for these c1 and c2 are the coefficients, and the coefficients can be obtained by putting or analyzing the boundary condition. The boundary conditions here are at x equals to 0, y equals to 0. And at this point at x equals to L, y is equal to 0. So you have two boundary conditions. This is second one and this is first one. So in this case, you can put these boundary conditions one by one and you can obtain the values of C1 and C2. So this condition, on the first boundary condition, you'll be getting C2 equals to 0. By applying a first boundary condition to this equation, you'll be getting C2 equals to 0, and for the second boundary condition, x equals to L, y equals to 0, you'll be getting 0 equals to C1 sine square root of p upon ei. 0 for y equals to 0, sine L equals to p upon ei. At this point, either C1 is 0 or sine square root of p by ei is 0. So now you can know that the C1 cannot be 0 because C2 is already 0, spot is already 0. So if C1 becomes 0, then your y is equal to 0, which is not the case. So either C1 is 0 or sine square root of P upon EI is 0. So in usual cases, we used to put sine square root of P upon EI approximately equal to 0. So with this condition, sine square root of P upon EI is equal to, this can be sine, in terms of sine, this can be equal to 0 only when your this theta can be is approximately equal to 0. That means square root of P upon EI, this is approximately equal to 0 for a case of sine, or they may be equal to pi, then also sine 180 degrees also 0, or 2 pi 360 is also 0. You know that sine curve is like a crest and trough and crest and trough in this way. Sine curve, sorry, in this way we know that sine curve is like this. So for each and every 0, pi, 360, in this way, each and every cases will be getting 0. So 0, pi, 2 pi and 3 pi and so on, you'll be getting 0. So that's why from this becomes a bit complex for you. So from this, if I put this here, it becomes a bit clumsy. So I'll be getting square root of P upon EI times L is equals to pi, or basically n pi, because this is 0, this is 1, this is 2, or so this is basically is equals to n pi. So from this we can obtain expression in terms of P, which is the critical load, and this is equals to pi square EI upon L square. This becomes my critical load that I have explained here. This load I have explained here. This is the critical load basically on this is a critical load at which your column will be going to buckle. So we'll talk about this expression more, and we'll see this, write down the load again. The critical load CR is equal to basically pi square EI upon effective square. And remember that this effective is written, and at I you can also write minimum. So a critical load for a particular column will be experiencing a modulus of elasticity E and I minimum. I minimum because for a particular column you may be having an XX, IXX, and IXX, this one, and IYY. So at IXX you may be having, or IYY you may be having. So whichever along against which the critical load is minimum, will take the I, that particular I, and the effective length is the amount of length that is actually used during the buckling of the column. So that is the effective length of the column. So this actually changes as the boundary condition of the column changes. So for a pinned support, this is a pinned support. We have derived this equation for a pinned support. So for a pinned support, this L effective length is actually the overall length of the column that has buckled. But for different cases, this length will increase or decrease for different types of boundary conditions. So as we are going to see in different cases. Further, remember that this pi square here is very important, because as you have seen in this case, sine square root of P upon EI. So this theta square root of P upon EI, as I said, that this is having this kind of a nature, a sine curve. So at each and every 0 and this is 180 degree. So this is 0, and this is at pi, this is at 2 pi, 3 pi, and so on. So the point is that here, that where it is. Okay, so point is that here at each and every pi, that means 1 pi, 2 pi and 3 pi, only at these locations this critical loading occurs. Within this, apart from this, during this band, during these locations, the buckling will not occur. The buckling is not supported. So the critical loads are only at the locations of pi to 0, at pi, at 2 pi and at 3 pi only, not at the other locations. So in this case also, this is for this particular pin condition I have written pi, but for the other conditions they may be changing. So as you can see, for the case of a pi, this is the case when we have a pin support and it buckles. So for the case of pi, that means theta equals to pi, that means theta means that square root of p upon ei is equals to pi, then it will take a full length as an L effective. L effective will be the full buckling length. But however, as the pi increases to 2 pi, then the failure mode may change and the failure mode may look like a bit different, and this may be in such a way. That means the effective length here is basically divided in two parts. So the buckling here shows different modes. In first mode, at a mode of theta equals to pi, this has shown the overall effective length of the buckling with one curl. However, in the other case, when theta equals to 2 pi, a 2 here kind of shows the sinusoidal nature of the curve. Here it shows the sinusoidal nature of the curve. So for in a similar way, for theta equals to 3 pi, the buckling nature will be, you are understanding it correctly, it will again show you a sinusoidal nature of the sine curve. Correct. With here, sinusoidal nature of, that means it has 3, 1, 2, 3, means 3 crest and toes, like we have in this case 1, 2 and 3 for the 3 pi. Okay, remember that the buckling modes will occur only in these conditions and the critical load will be for these particular modes only. So failure will occur only with these particular modes. For theta equals to pi, the failure can occur only in this mode. For theta equals to 2 pi, the failure can occur practically in this shape. So the bending of the column or the buckling of the column may occur in this shape. Similarly, for 3 pi, the buckling can occur in the sinusoidal mode again. So as you can see, the effective length, overall effective length is same. So this is the overall length, effective length. In this case, the buckling occurs in this length and in this length, so the overall effective length again is same. And in this case also, the buckling occurs in this length and this length and this length. So the overall effective length is same only for different failure modes. So where does the effective length actually changes? The effective length is directly related to the boundary conditions. Boundary conditions. Now we'll be talking about different boundary conditions that a column may experience. We're talking about the effective length of the column. So different end conditions, what will be our case? So one of the case may be a pin case that we have taken. So in a typical pin case, in which a column is kind of a pinned at both the ends. So in this case, as I have seen, my buckling occurs in this fashion only. So my effective length was the overall length of the overall length of the column. So my L effective here is the overall length of the column. In another case, let's say it is fixed in both the conditions. Let's say a beam is kind of fixed in both the conditions. So in this case, this is hinged or pinned. both ends, ठीक है, and in this case both ends fixed, like in this case. So in a fixed case, as you can see that the rotation here is not allowed. So particularly from here the buckling will start from the middle and will take the shape in a roller coaster form. So effective length of buckling is actually the effective length that actually buckles it is usually is only half, and you can also drive this. You can also drive this. Only the effective buckle length is only half. Half means the 25% length is gone just to take care of this boundary condition, 25% gone here to take care of this boundary condition. Only the effectively only half of the length only buckles. In which condition? In which both the ends is fixed like this. What is the difference in both the conditions? Here the rotations are also not allowed. In the pinned cases, here the rotations are allowed. Here the rotations are also not allowed. In the another case, one end fixed and one end, in this case, like this case, in one end in which we have a fixed one end and free one end. So in this case, the effective length actually, again, it goes like this only, and you can also mirror image to the other side to take up the overall length that actually is the effectively like this. Now it's very important here. Just look at this condition. This is one end fixed and other end free. One fixed, other free. What happened in this condition? This is one end fixed condition and then this is free. So now just first of all think a situation in which a column is like this. Think a situation, or one of the very common situation in which we have seen like this is a submersible pump. A submersible pump is like, if I rotate it, then this is my earth on which my submersible pump is placed, and then my column or long rod goes like this, or a pipe. This is, sorry, this height is around, in here in our cities it is around 200 feet. So around 200 feet, this is definitely a long column. We have a submersible placed here that actually takes up the water and pushes it on the top. So this end of the submersible is free. This is a free end, and then the water goes up, and this is the fixed end because it's connected to the earth and been fixed here, and then the pipe comes out from it, and then you can take it afterwards. So this is one of the conditions. This is fixed and this is free. So if you take the effective length, so effective length, this example is important because you will be questioning the value of the effective length here. You can derive the effective length by using the same conditions that we have seen, but how will you justify this, that the effective length is 2L? As I said, in this case the effective length is L because the rotations are allowed. In this case the rotations are not allowed. That's why the effective length has actually reduced by 2, because 25% length is eaten up at both the ends. What is the reason here? Here the length is also eaten up, but as you can see, as I'm giving the condition that it is the buckling part, or this part actually, this is the deflection that occurs, or the amount of buckling, or the amount of eccentricity that is offered by the column. So that you have to take on the other side also to make this symmetrically same. That's why the effective length is double the length of the column. In the another case, one end fixed and another end hinged, we can have another condition in which this is hinged and another is fixed like this. So again, this is fixed and this is hinged, so it will take full length, and then this is not allowing it to buckle. Fixed end is not allowing it to buckle. So this actually, only this effective length is L effective. So again, approximately 25% is eaten up. So L effective will be equals to L by square root of 2, 1 by root 2. Root 2 is approximately 1.7 times. So you can inverse it, you can see that's approximately 70% effective length is available to you. So these are the boundary conditions for different conditions. So you will, in the problems, you will be given different examples, and on the basis of these examples, you will be categorizing that column in one of these four conditions. Usually these are the most common four conditions of the column. So you'll categorizing the problems in one of these four conditions and then putting yourself here and put the effective length as these values, because the effective length is this, and then use the formula of Euler, pi square EI upon L effective. Put the effective length for the particular boundary condition, take the minimum Ixx moment of inertia, Ixs or Iyy, and take the material constant you will be having. Secondly, condition for the buckling mode, as I have explained already. For different buckling modes, the pi, because this is n square pi square, so n will be different. This is n pi, here n is 1, here n is 2, here n is 3. For different failure modes, the modes will be, the buckling or the kind of a curl that we are experiencing will be different. So this actually will be more clear in some of the numerical problems that we're going to do. We'll be going to show you some of the numerical problems. Further, so we have already gone through most of these topics, and I would like to go through this slenderness ratio once more. And slenderness ratio and the Rankine theory, basically we'll be discussing these two together, and we'll be seeing what effect it produces on the columns, slenderness ratio and the Rankine theory. So stay tuned for the next video. In the next video, we'll be discussing these two topics, and we'll be continuing from here only.